In this video, we are going to talk about vector spaces, and this is mostly kind of how I look at them, the applications, and how I get an intuitive feel for vector spaces. First, we should just review what we know about vector spaces and our current examples of vector spaces, but then I'll talk about other spaces and how to kind of look for them or what to see. And then later we'll talk about waveforms and how they make a vector space, and then we'll go on to an analogy, which is actually more than an analogy, it's an example of colors as a vector space, and this is where I get a lot of my intuition, or not intuition, but a good feel for what's going on. So first, just to review, a vector space is a set of elements that we call vectors, so a set of elements, and then with that set of elements we have an addition operation, and we also have a scalar multiplication operation, and these two operations satisfy these 10 properties, 2 of closures, 4 of properties of addition, and 4 on properties on the scalar multiplication. When they satisfy these 10, then we say that the set of elements along with the 2 operations form a vector space. And our examples, or one of our main examples that is also good for our intuition, is Rn. And the reason why I say it's our main example is because you're somewhat familiar with them. You've probably worked with them before in physics or vector calculus. Other examples we looked at in a previous video is a set of all 2 by 3 matrices with real entries. We looked at the set of P2, the set of all real polynomials with degree 2 or less, and as you may have guessed, this could have been P3, P4, P5, Pn essentially is a vector space. And then last, we looked at, we did an example with the set of all continuous functions on an interval AB. There are many more examples of vector spaces that you can find, but for whatever reason, when I pull out a vector space from a textbook and we start talking about numbers or functions or polynomials or matrices, people aren't, I feel like a lot of students don't appreciate how widespread vector spaces are, so we will talk about that with a couple of other examples. And to start with, I'm going to mention a project that I used to give students when I was teaching. And this project is, I would tell them to go out and look for a vector space or create a vector space. And then I feel like it was a good project because it gave people kind of an idea, or they would think more about what it meant to be a vector space. And I have a couple of examples that some students had given me, which I thought were kind of creative and that I still remember. And the first one is the Rochambeau game, so we should look at that. And also the other one was from cooking, and it was spices. Rochambeau is the commonly known game where you have these hand positions that designate a rock, a piece of paper, or scissors. And the idea is 2 people will say Rochambeau, and then on bow they put out their hand signal. So they either put out rock, paper, or scissors. And the idea is that paper can cover rock. So if someone has a rock and someone else has paper, then the paper wins. However, scissors can cut paper. So if the 2 symbols put out were scissors and paper, then scissors win. However, a rock can pound scissors. So if these are the 2 symbols put out, then the rock wins. And so this is our addition. So rock plus paper, it's paper that wins. Rock plus scissors, it's rock that wins. And if it's paper plus scissors, it's scissors that wins. So that was our addition operation. And then, so that was kind of an interesting start, and I liked it a lot just because it was interesting, it was memorable. So what about scalar multiplication? Well, that, I think, so somehow we have to come up with a definition for scalar multiplication. So if you have 2 times one of these vectors, what does that mean? And then I think the students were talking about you could place bets. So the scalar was about bets. So if you put 2 paper, you were willing to bet $2 or something. So it was an interesting way of trying to work it in. Another person said, well, maybe it's the number of times, if you want to play 3 games, although this doesn't make a whole lot of sense, but they would say they would throw out 2 scissors, that meant they were going to play scissors twice in a row. But it was some sort of weighting that they were doing. And then closure. So that was another problem. They needed some sort of the the additive identity was the problem, because in this game, there's no hand signal you could get that would always give back what the other person threw out. So like if you did, so what you want is something that, let's just say there's this fourth hand signal, then no matter what comes up, it's always the other thing that wins. And I think what this group said is, well, maybe if you're playing against some child and you want them to win sometimes, maybe you'd be willing to throw the game. So there would be like this extra hand signal they would come up with. Maybe it was L for loser or something. And whenever you put out the L for loser, you would automatically lose. And so rock plus loser would be rock. Paper plus loser would be paper. And scissors plus loser would be scissors. So it was interesting. And you know, as I said, this game doesn't naturally form a vector space, but this group did go through and tried to see how it could be altered, so it did. And that exercise just kind of made them think through what all these properties meant. Another memorable one was spices. So, you know, you can combine spices, so that would be the vector addition operation. You could have scalar multiplication where you put in a lot of a certain spice, but you know, exactly what would addition look like? Salt plus pepper equals. And so they had to define it, and I think they took a limited number of spices and then they kind of circularly defined them so there would be closure. But then, you know, what was the additive identity? They might have used salt for an additive identity, and they argued that it didn't so much change the flavor of things, but it enhanced things. So that was kind of an interesting take on that. But again, if you were just talking about foods in general, someone else said, well, maybe if it was foods in general, maybe the additive identity would be something that cleared your palate, like a sorbet, or maybe it's like coffee beans, which I think you're supposed to smell when you want to have a neutral smell. But again, it wasn't so much that spices were in fact a vector space, but just looking at it and going through the exercise of figuring out how can you define the addition operation, how can you define scalar multiplication, and what are the problems, or what kind of things do you need to adjust to make it a vector space. It was interesting. The projects that ended up being the easiest to represent or claim to be vector spaces were those of waveforms. So, and in fact, waveforms, along with the normal addition of vector waveforms and scalar multiplication of waveforms, do indeed form a vector space. So we should look at that, and to start, we have to understand how to add two waveforms. So if we have two waveforms, I have one in blue and one in green. The way we add the two waveforms is essentially point by point. So in other words, here at x equals 0, both the blue and the green waveform have a y value of 0. So our addition will start at 0. Over here at x equals 1, we have the green waveform has a value of 1, whereas the blue has a value of 2. So we add them together so that our resultant vector is going to be at 3. X equals 2, we're both back at 0. And then over here at x equals, this is what, 2.5. We have both values at -1. So now our addition is going to be down here at -2. Over here, we're right here because, let's see, at x equals 3, the green is at 0, so then it's the blue waveform contributing. And then finally, at the very end, we get this 0 again. So our addition vector looks like this. This looks like a little funny. Somehow it gets up to there. So it's sort of this kind of point-by-point sort of way. That's vector addition. Scalar multiplication, on the other hand, let's say we have this black waveform, and that's our original waveform. If we want to multiply it by 2, we take each height and we multiply it by 2. So here at 1/2, we have this 1/2 height, so when we multiply by 2, we're going to hit 1. Here we're at 0, so we're at 0. Here we have a height of -1, so when we multiply by 2, we get to -1. So this blue represents 2 times this black waveform. Now that we have our two operations defined for waveforms, we can start looking at our properties. For closure, well, we can see, also this is illustration I forgot to tell you. We have a blue waveform, a green waveform, and then we add them two together to get the red waveform. But anyway, the addition of two waves kind of you always get back a waveform, so it's closed. Scalar multiplication, again, you always get another waveform, so scalar multiplication is also closed. Wave addition is commutative, like you can see, because you're adding point by point. It doesn't matter if you consider the blue the first waveform or the green the first waveform. You can convince yourself addition is associative. The additive identity, well, if you want to add something to this this black waveform and not change and get back the black waveform, then you're going to add the zero vector, which I just drew in yellow. So, or the waveform is equal to 0. The additive inverse, so if you have this blue waveform over here and you want to get to a flat line, you're just going to add this, if you're looking at the black, to get the inverse, you're going to add the blue. And then, in other words, you're just going to reflect the black waveform over the x-axis. So when you add them together, you just get the x equals 0 line. You can go through the properties of scalar multiplication and kind of convince yourself that they will all work out as well. And the waveform is a very important vector space because so many things can be represented by a waveform. So light and color, they actually are waveforms. Sound is a waveform. But you also even can represent things like amount of rainfall as a waveform once you just plot it. And from these, my favorite one to think about, especially as we go forward, I use this as kind of my analogy or my tool to visualize things, is colors. Again, colors can be represented by a waveform. But you can see but I can also think of it as mixing colors. So my vector addition is mixing two colors. So for example, red plus yellow will give me orange. And then you can see I can say 2 red plus yellow. That'll give me a darker, redder orange. This combination, this addition or combining of colors will be commutative, right? It doesn't matter if I put the red or the yellow first. It'll be associative when I mix 3 colors. The additive identity, so that one's tricky. So certainly if you think of this as waveforms, just light in a wave, then that's easy because then you have the 0 waveform. If you're thinking of this as paint, then you need some sort of neutral paint that can mix in that doesn't change your colors at all. Additive inverses, so again, this is also, if you think of this as waveforms, it's easier because you could say, okay, when I add red to its negative, then I'm going to get back a 0. If somehow I can subtract out red from my colors. Very easy to do with light, not so much with paints, but if you could with your paints, just subtract out a color, that would be your additive inverse. And then you can also convince yourself with scalar multiplication, that's just adding more units. If you think of, there's a unit of red, and you can add 2 units or 3 units. You'll see these properties will also hold. And when we go forward with this, we'll be studying other things in vector spaces, and we'll look at a concept called span. And, using colors as our sort of example, it means with a given set of colors, what colors can you make? In other words, what colors does your set span? So in other words, if my set of colors, the one that I'm carrying around in my backpack today, are red and yellow, then the span of my colors, what colors can I make, would be red, yellow, and orange, because I'm going to use some sort of combination of red and yellow. Whereas if the next day I carried around red, yellow, and blue, all of a sudden the span of my red, yellow, and blue colors would be all colors, so that's pretty powerful. This also gives us a way of looking at linear combinations, because orange now we can say is a linear combination of red plus yellow, whereas red is not a linear combination of yellow. We could say red is a linear combination. We could say red is equal to orange minus yellow. Remember, we want to be able to take colors out. So we do have this inverse idea, right? And we can also put a little, if we want dark orange, we can put 2 times red, and this would be 1 times yellow. So orange is a linear combination of red and yellow, and red is also a linear combination of orange and yellow. But orange is not a linear combination of blue with yellow. There's no way we're going to get orange out of blue and yellow. And then we're going to ask, because, 3 colors gives me all the colors. So what is the smallest set of colors, and this is also called dimension, that you need in order to make all the colors? So we can have red, yellow, blue, cyan, magenta, yellow. It's always 3. Once one basis is 3, then all the bases for that vector space is 3. So these are ideas we're going to develop formally, but this is just to give you a feel for what's going on. I just want to go from colors now to Rn. So let's say we have one vector, and that one vector can span a line. Let's just say this is my vector, right? I can't add it to any other vector. There's only one vector in my set. So that's the one vector. So what can I do? I can scalar multiply, and I just get a long line. It represents a line. And again, at this point, I'm not talking that this one vector represents a whole vector space. Rn is a vector space. I'm just saying, what if I have a subset of Rn that's one vector? Then what does it represent? It represents a line. And again, even the colors, when I'm saying I'm carrying around yellow and blue, I'm not saying yellow and blue represents a vector space. It's all the colors that represents a vector space. It's just that I happen to be carrying around yellow and blue. So here I happen to be carrying around one vector. What can I represent with it? I can represent anything on this line because I can scale it. What about two linearly independent vectors? What can I represent with that? So here, if I have two linearly independent, and we want them to be linearly independent so they're not collinear. So I have two vectors that are not on the same line, right? So I don't want the case to be, my second vector to be this blue vector along with the black vector, because they really sort of represent the same thing. So here I've moved my drawing over with two vectors, v and w, to see what two non-collinear vectors can span. Using the parallelogram law, when I add to these two vectors, what I get is this point here. If instead I scale v, so it's something a little bit shorter than v, and scale w, so it's something a little shorter than w, what I am going to get is a point interior in this parallelogram that v and w kind of define. Here is another scaling of v and another scaling of w, and you can see when I add them, again I get a different point that's interior into this parallelogram. And all these scalings, these different scalings of v and w that are shorter than v and w, will give me all the points inside this parallelogram. And now you can start scaling v so it's a little longer than v, and w, so in this case it's a lot longer than w. And what you'll see is you get this point way over here. So it's sort of like extending the parallelogram of v and w. A different scaling of v and w, again, where v is a little bit longer than v, w is a little bit longer than v, you'll see you'll get something. Again, the idea is you're extending this endpoint here further out, this endpoint that the parallelogram described by v and w, you're extending the edge of it. Here's the case where v is shorter, but w is longer, and you can see we get this point here. And now I've made w a little bit shorter, but v a little bit longer, and we get this point over here. Again, all the scaling of v longer, w longer, it's like getting all of this now, like a bigger parallelogram. Similarly, now if I think of scaling v in the negative direction and adding it to w, I'm going to get all of these points kind of in this span, in this part of the span of the negative v w rectangle or parallelogram. And when I scale w negative now, and I add it to v, I'm going to get this part of this parallelogram. And then last, I have negative w and negative v, and I get this part of the parallelogram. So essentially what you end up at the end is you get the entire plane. So that's why with two linearly independent vectors, I can span a plane. And with three linearly independent vectors, I can span R3. So why here do I say linearly independent vectors? Well, for the two, it's because you don't want them to be collinear. But the idea is If the vectors are linearly dependent, there's some repeated information. In other words, one of the vectors, if they're linearly dependent, at least one of the vectors can be written in terms of the other two. So that one vector that can be written in the other two, its information is already contained in the other two vectors. So in terms of the colors analogy, if I had the three colors orange, red, and yellow, the orange doesn't really help me reach other colors because its information is already contained in red and yellow. In other words, orange can be made from red and yellow. Orange doesn't help me make additional colors that red and yellow don't already allow me to make. So that's the idea of span. What are the new colors you can make, or what can you reach with the vectors that you have? Extending this idea is the idea of a basis, which is the smallest set of colors you need to make all the colors, assuming we're talking about colors as a vector space. So a basis for all the colors would be red, yellow, and blue. So you need exactly 3 vectors to make all the colors. So an alternate basis for the colors would be cyan, magenta, and yellow. And that's it for this video. I hope you found it helpful, and thank you for watching.